Kaifu. All right, good morning, everybody. It's great to be here. Before I get started, I wanted to see a quick show of hands. How many of you are doing your masters and PhDs? And how many are doing your bachelors? And how many are in industry? And how many don't know what you're doing yet? I also want this to be interactive, so I want to make sure that if anyone has any questions along the way, please do stop me and ask me, and I'll be happy to answer them. Today, I'm going to be talking about a very fascinating topic. It's plumbing. This is not plumbing for water, but this is plumbing the web. The real question is, how is the web going to evolve from a standpoint of folks putting data into the big cloud in the sky? How do people get data out of it? And what is Google doing in this regard to have very good APIs? And what are the platforms you're building to support a lot of these third-party applications? That's going to be the primary focus of my talk. I'm also going to give you an insight into a lot of what the back-end systems look like. So once we have all the data stored in the cloud, how do we manage all the data in the back-ends, and how do we allow people to process them in an efficient fashion? So in addition to the Developer Day here in Beijing, we also have Developer Days across the world. There's another one going on in Mountain View in a few hours. And you can see it's pretty much all across the world, and we're excited to be in Beijing to talk about our longer-term plans, as well as to see how we can get more of you involved with some of our APIs and our platforms. So here's a quick look at how our API strategy has evolved over the last few years. In 2002, we had a very primitive set of APIs. We had Google Search. And one of the things that we had was we had a simple SOAP API. And it was very primitive in that you could do a simple set of queries. And we had a lot of rate limiting. So no one could do too many different queries. And over time, it has evolved and has had more features added to it. And at some point, it sort of got a little bit stale. In 2004, we launched our desktop API. This is a lot of the client software that we have, and how do people access content within their clients. It's in 2005 that we really started pushing heavily on having a much more of a platform in terms of having people store more of their content and access the data that they have been storing into us through APIs like the applications we've had, our Gmail and Calendar and so on. So we started investing a bit more into that. So in 2005, we launched a couple of APIs, the Sitemaps API, which I'm going to be talking about quite a bit, and also the Gadgets API, and also the Maps API. 2006, you can see a whole bunch of announcements. We improved our search API quite dramatically and made it much more AJAX friendly. A lot of work on Google Web Toolkit. You'll be hearing about that in a session later today. Calendar Data API, and also a whole bunch of data APIs for our different products. And June will be giving a talk about the GData API later today. In 2007, this year, we've done a bunch of work around adding even more APIs, including maplets and gears, which I'll briefly talk about later. So one of the questions that we keep asking ourselves is, how much information is really out there? Because we want to make sure that we, as a company, can scale over time to have more data hosted with us, and also have very efficient and scalable APIs to access a lot of the data. And one of the largest data sources is, of course, the web. This is where our roots are. We started the company a number of years back, Larry and Sergey did. And at that point, even when I joined the company, I think we had maybe 25 million web pages, which seems like a very small amount today. At that point in time, it actually was a lot of data. Now it's in the hundreds of billions of documents. And the amount of data that we have is growing so dramatically every single day that just on the web, we need to do a lot of interesting things just to scale. And I'll be talking about some of our work in how we improve comprehensiveness of Google search results in the next few slides. When you switch away from just the web to all the personal content that people have, including their email, as well as their content on their desktops, as well as closed databases, the amount of data just explodes. It's in the petabytes, hundreds of petabytes of data. And the Library of Congress, which has a lot, this is the US Library of Congress, which has a lot of the books, doesn't have as much data. So a lot of what we're talking about is how do we take data and how do we make it easy for anyone who wants to store large amounts of data, as well as interesting metadata in the cloud in the sky, and how do you offer interesting APIs so that it's easy to get access to your own data. So any questions at this point? All right. So I want to talk about early search. The amount of data, as we just talked about, has grown quite dramatically. But fundamentally, the way in which search, Google search and Yahoo search and MSN search and Baidu search, all of them work is in a very similar kind of fashion. There are a lot of web pages out there. And what a crawler does is there's something known as a web crawler. What it does is it starts with a whole bunch of pages, seed pages. It could start with cina.com.cn, or it could start with yahoo.com, or with Wikipedia, or any of the other sites, and start crawling more links out of those pages. So you download a page, and you parse the page, you extract all the links out of the page, and then you have more links to go and crawl. So that's typically how a crawler starts operating. And once you have a whole bunch of links, then you add it to, think of it as a queue. You add it to the end of a queue, and you start processing more of these pages and downloading even more of the content. And so essentially, you just sort of cover the entire web graph to access every single page that there is on the web. That's the crawling process. That's from all the web pages. Once we have all the web pages, the next step is to figure out how do we take the most interesting parts of a given page? How do we annotate it? How do we extract useful metadata out of a given content? How do we extract anchor text? How do we extract font sizes? A number of different signals that go into constructing a very nice index. An index is really, think of it as a dictionary that maps from a given sort of words or phrases to a list of documents on the web that have that content. And once we have all that, we throw all that index information in some efficient data structures along with that into a whole bunch of machines. And when a search comes to google.com, we go and access the index, and we return back to you the most relevant results we can find. So this is how early search has been operating for the last few years. So one of the things I want to focus on is how the link extraction actually works. So I mentioned that you need to have a link to a given page. To identify more pages on the web that you want to throw into the index and make it available to the users, you want to make sure that the page has an incoming link. There is a hyperlink that links from one page to another. So this is actually how the web has worked. But the problem, as you might all imagine, is it doesn't work very well for dynamic content. It doesn't work for Flash. It doesn't work for Ajax, because no one really links to a page that says dynamicpage.com/search query equal to Beijing. No one links to that kind of content. So there is a huge amount of uncrawled content on the web that none of the search engines have been getting to so far. And this is partly because of a fundamental problem that we have with the web. So a couple of years back, a number of us in a few different offices in Google, and this is in Kirkland plus in Zurich, we started working on how do we build out a web server and search ecosystem. Rather than us going to a web server and looking at the top level page, extracting all the links, what if the web server told us what they had? So conceptually, in the Unix world, it's ls. If you have a listing for all the content that you have on a given directory, similarly, why can't that concept be extended to websites? And you don't just want to have a listing of all the URLs. You also want to have a listing of all the last time a page actually changed. So ls minus al, so that you can know when was the last timestamp of the page changing. And think about it. The web servers typically have this kind of information. They know when content has changed. They have an Apache they have an Apache web server running, and they typically are virtualizing all the file system to make it exposed. And so they have this kind of information. So we started thinking about what if every web server started giving us this information? That's part A. The second part of it is feedback to the web masters and web servers about problems. In the previous slide, you notice that it's very directional. You have pages on the web, and crawlers just come along, and they crawl, and they find content, and they keep indexing it and moving along. But there's really no mechanisms right now on the web to make it easy for crawlers to give information back to the webmasters and the web servers, saying that you have 43,000 errors because the last time I tried to crawl where your DNS was down, or your robots.txt file, which is it's a web standard for exclusion of content. It actually precludes us from crawling your web pages. So a lot of this information is just not available. So we started thinking about how do we build out this web server search ecosystem so that we can get, and not just us, all crawlers can get complete comprehensive information from web servers, and also us giving information back to the web masters and servers so that they can do a better job of giving us all the content. So this is one of the interesting APIs that we have at Google. So sitemaps is really LS for the web. So every web server or every web plugin that exists out there can compute these XML documents, XML sitemaps, that are auto-produced and are maintained on the web server. So think about it as on example.com / you have a pointer to a document or a file that has a listing of all your content. And some of the attributes I'm listing over here are simple things like URL. Tell us what URLs you have. Change rate. When is the last time, what is the expected rate of change of this content? In a lot of cases, many companies have archival content, or a lot of libraries have archival content, things that haven't changed in the last 5 years and don't really expect to change again. So why should we crawl them? That doesn't make sense. So tell us about it. Last modification, the last time the page changed, and that's another useful signal that web servers can compute and give back to us. And priority. Right now, the way in which crawlers typically work is they have finite bandwidth. They can only crawl a certain number of pages within a given site before the site has, they have to pay too much in bandwidth, or they don't have enough capacity. So priority, if we had to crawl your web pages, tell us roughly what are the list of, how would you prefer us to crawl this? All these are hints, all these are optional. But the required element is really the URL. We want to be a lot more comprehensive. So we launched this about a couple of years back, and and one of the other elements we added recently is auto discovery. So robots.txt is the exclusion protocol. It says that it's typically on every single website. It has information on a per crawler basis that don't crawl these subdirectories, or please crawl these subdirectories. So we also added auto discovery so that you can link to your sitemap file from the robots.txt file. Another element of the protocol is it's actually a log structured protocol, in that there's a notion of a dictionary or a meta sitemap or a sitemap index file, which allows you to add incrementally as many sitemaps as you want to over time. So it's log structured, that you can make up a big sitemap with 50 million URLs, and you can add another sitemap which has modifications of that sitemap metadata that you want to offer to us. And all this is fed into our crawling system. And the protocol also is structured so that it's scalable. So you have 50 URLs or 50 million plus URLs. You can tell us what you have and give us metadata. And some of the interesting things we've noticed is that, especially for a lot of the dynamic content pages, by giving us information about when is the last time they changed or the expected change rate, we can actually reduce the amount of crawling that we do on a given site by up to 2/3, by up to 66%, because in a lot of cases, pages just don't change. So what's the point in having server resources on the crawler end as well as in the web server to interact about whether a page has changed or not? So that's the high-level overview of sitemaps. And in terms of adoption, what we did was we thought it was an interesting idea, but we didn't know how the web was going to react to this. So we launched this as an open protocol in June of 2005 under Creative Commons 2.0, and very similar to how RSS really works. And also in November, we started working with all the other major players in the industry, with MSN and Yahoo and so on. And we announced joint support so that if any web server or any web plugin computes a sitemap automatically by the simple plumbing mechanism that has been missing on the web, then all of the search engines and any of the other search engines any of the other application that you want to build on top of web pages can use this. And a lot of this information is available on sitemaps.org. Unfortunately, the color is in yellow and it's not very visible. But sitemaps.org is a great place to go and get more information about the protocol and how to build out APIs and support for web servers to give information to make us a lot more comprehensive. Also, in terms of adoption, we've had billions of URLs that have been coming to us through servers and tools and plugins. IBM recently announced that they're going to be supporting sitemaps natively in all their enterprise software, like WebSphere and Portal and so on. So that's the sitemaps part of the equation. So the picture again, early search was really about search, link extraction, and web pages. And what we're trying to do is to get to a point where our biggest application on Google.com, which is search, becomes a lot more comprehensive. And by adding the ability for web servers and plugins to give us information about what they have and us giving feedback about what we find in terms of problems on their site. And also the way in which we did this is in a very open way. We did not want to, we prefer to do, in Google, we prefer to launch protocols or support for protocols by working with industry. And this is really what we've done, because the entire web just benefits from some of this functionality. Any questions about sitemaps, about search, before I switch into other APIs that we have for developers? No questions. All right. I hope I'm not putting you to sleep. So, talked about search. We have a whole bunch of other applications in the context of Gmail, calendar, maps, and a whole bunch of other things. So what we really try to do in these consumer-facing applications, as opposed to the search-specific application, is three different mantras that we have. How do we integrate all our Google services? When you have data in your docs, or spreadsheet that you host on Google.com, and you want to have it available for you in Gmail, or you want to have a linkage between Gmail and Calendar, how do we really integrate Google services, and how do we offer a platform so that you guys can actually go and develop on top of this platform? Reach. Once you have a platform, you want to make sure that there's an easy way in which you can reach a lot of consumers very quickly, because that's where innovation actually starts to kick in. You can try out lots of ideas, and you can see how people react to it before you can make interesting products. And also, what are the tools that we offer to build out these next generation web apps? So this is these three different mantras that we are focusing on to build out all our consumer-facing applications over the next few years. So I have a few examples. In the integration block. When we launched our web API for maps, we actually hadn't even launched it. Someone noticed that there was an easy way in which you could take Google Maps, and it is an internal API, but it's kind of exposed on our external site. They noticed that they could take the API that allowed them to do a lot of interesting, cool mashups with maps and impose more data on top of the maps functionality that we had. And a lot of sites started showing up on the web. And this is really when we really started to think heavily about our platform strategy, as well as our APIs and our platforms. So here's an example. This is a site that Google would never build. It's called Walk, Jog, Run. This is a person who, if I remember correctly, he wanted to communicate to all of his friends as to what are interesting paths that he could take to run in a given area. So this was really done by a simple API, using the Maps API, imposing some data that the individual, the user, actually had to make it available to his friends. Another example is actually imposing housing data on top of maps. You can start seeing that there are a lot of different ways in which you can start using maps. And it's not just maps, there are lots of other things you can do with our applications too. Here's another example where it's more about imposing movie information and review information onto maps and making that available to folks. So a lot of these are really about taking existing functionality that Google supports and layering on top of it some data that makes it much more compelling and interesting to some other group of individuals. Here's another one. We have an API for Picasa. June is going to talk about the GData API, which is a mechanism through which you can interact with lots of different products. And this is another third-party site. Picnic decided to make an interesting set of applications on top of Picasa. Here's another one. There's a calendar application. So we have Google Calendar. And here's using the GData API. There's a third-party software that came along and said they wanted to do some syncing of calendars. Another one. So there's a lot of possibilities, and the only barrier here is your creativity. You can take any of our data sources and mash them up in interesting ways and build out a cool application that uses a lot of the backend functionality that Google already supports. So now that you've done the integration, there's an issue with reach. So let's say that you have a very cool idea and you built out a cool mashup of different content. The next question to ask is, how do you get distribution across to a larger consumer population? And here is a case where either you could just send it to your friends and it'll be viral and it'll grow in an interesting way, or you can also use our iGoogle platform, which is a mechanism through which you can add little gadgets, which are easy ways of offering some interesting mashups to a large audience. And a lot of the gadgets are listed on the gadgets homepage. If you go to google.com/IG, you'll see a lot of this information. So it's a nice way to promote very simple applications that you have built to a much larger audience. Here's an example of different gadgets that people have made up. There's a person who is interested in National Geographic, another one who's interested in Google Finance, and another one wanted to have a simple way in which they can have notes. So they can have a to-do list, and they can store that information into the cloud and have that accessible through their iGoogle page. And this is another gadget. And in this one actually got, I think, about 5 million page views in the last week. So which is pretty, in terms of reach, it's pretty compelling and pretty comprehensive. And this one got another 6 million page impressions last week. So it's another gadget, again, using the same technology and APIs. Now that you've talked about possibilities in terms of you can take our simple APIs and you can start mashing up different content and making it available to a larger platform. So that's two parts of the equation. The third part is, how do you build very cool Ajax-y applications so that you can have a much more interactive experience? And a lot of that will be discussed today in a talk on the Google Web Toolkit. So this is a simple way through which you can build out very dynamic applications using a higher level language like Java, rather than having to worry about cross-browser platform issues and the inconsistencies that they have. Firefox does certain things differently. IE does things differently. So GWT is a great way to is a great platform for building out these interactive applications for the web, which you can clearly build out and then have it become a gadget and reach a lot of people as well. So that's the story around our APIs. So before I switch to a lot of the things we do behind the plumbing, I wanted to stop and ask if anyone had questions. No questions yet.
像大家可以用那个中文提问，如果那个用英文提问不方便的话，可以用中文提问。I think audience will be easier to ask questions in Chinese.
Okay.
有问题吗？如果现在没有问题的话，待会儿那个Shiva也会留一些10到15分钟的时间供大家来提问和讨论。Okay.
So, any questions in Chinese? That, or should we wait? Okay, this question over there.
有话筒吗？麦克风。Okay. Okay. It's actually reaching.
Oh, very good.
Okay.
The question is a very good question. It's about, is Google doing anything for users, Gmail, Calendar, etc., who are disconnected from the web? So essentially, are we doing a lot of work in having offline access to a lot of your content? It's clearly a very interesting problem, and we're certainly working on it. And there's nothing we have to announce at this point, but hopefully we'll take more of your feedback and support a lot of that functionality very soon. Okay, so I'm going to switch back to the slides, and it seems a bit tricky. All right, so behind the plumbing. So we've talked about a lot of the applications that we have in Google. A number of you have actually used a lot of apps. So let me ask another question. How many of you use our core search on google.com? Quite a number of you. And how many of you use our other products like Gmail or Calendar? Okay. So a lot of the apps that we have are built on top of these APIs or standards. Like, think about things like sitemaps to help you in search, or think about the Data API to help you with accessing and storing a lot of your content on this large amounts of data that we have in the cloud. And a lot of these things are built on top of a couple of very interesting parts of the stack that we have in Google, which is the systems infrastructure, as well as the hardware platform that we have to make all this very easy and scalable and reliable. Every year in Google, we see an inordinate amount of increase in computational requirements in terms of there are more queries coming in, there's more data coming in, and there's much better results that we need to support. And a lot of this is there's a feedback loop too, because we want to make sure that we can build out better search results by taking a lot of user data and trying to improve how we improve the quality of results, as well as how do we make the experience even faster for users. So a lot of these requirements drive our hardware design philosophy. We made a decision very early on that we wanted to invest in very low-end server and PC class designs and just build lots of them. So this was in direct contrast to what a lot of other companies were investing in, which was to buy these ultra reliable and expensive hardware. And the problem that you end up having, as most of you know in computer science, is that pretty much every single component in a computer, no matter how reliable it is gonna die. Either the hard drive dies, even if it's more reliable, or the memory has some problems, or the power glitches. So a lot of companies invested on the hardware in terms of buying these ultra expensive hardware, and in fact, a lot of the companies ended up going bankrupt because they spent so much money on this. We had a very direct alternative to that, which was to build these very low-end PCs with the assumption that pretty much every single component that we had would have a fault, would have a problem. And we compensated for a lot of that with software. And that's what I'll be talking about in a couple of minutes. Also, given our incredible computational needs, pretty much a single machine or a single node with some amount of horsepower is not really that interesting. Pretty much all the problems that we have to be partitioned, have to be partitioned across lots and lots of machines, across lots of different data centers to solve these harder computational problems. And Also, the other point is that ultra-reliable hardware is really a myth. And we, rather than spending lots of money and compensating for that, we just wanted to buy cheap hardware off the back of trucks and just build it out and build out a software layer that will compensate for a lot of these things. So this was google.stanford.edu in '97. It's a small number of machines. And so all these were fitting under Larry and Sergey's desks. A lot of these disks were, in fact, bought off the back of trucks. So that's the only cheap, they only had a few dollars to spend, so they ended up buying very cheap hardware from them. So this was in '97. This was this was on the Stanford campus. This was in '99. So one of the observations we had early on was that all the hardware that we was going to be replaced anyway, because the hardware was going to drive, the hard drive was going to die, or the motherboard was going to have a glitch. So we wanted to have a very simple way in which we didn't have to take out a chassis, unplug the chassis, and take out the motherboard and take out the disk and put the disk back in. So this was really an alternative design to make sure that it's very easy to take out entire machines. So this is really a machine. You just see 6 machines right there. And all these things were mounted on top of cork boards. So cork, as in very inflammable materials. So this was the design in '99. And then the Santa Clara Fire Department noticed that that these things were getting very hot and were very bad fire hazards, that they pushed the company to have slightly more professional and slightly more expensive hardware designs. So this was in 2000, and you can see a data center. A number of you have seen these kinds of pictures. It's typically a rack. You have a lot of machines with a lot of these dual CPUs thrown into the mix, and maybe 5 disks or 4 disks that is in every one of these machines. You can still see that in a lot of these pictures. You can see the yellow wiring, which is still not very, it's still very ad hoc. We used to just have people move around the cables, and it was fine for us because we knew the software was going to compensate for all these problems anyway. And you also see a very high-tech cooling equipment in this picture. It's the fan at the bottom. That's how all the machines actually were cooled, because of the heat that they were producing. This was in 2001. It got to the point where machine construction became a part of the company. And so we would take in a rack in a given day, and then at the end of the day, we would just sort of have these machines come in and be plugged in, and all be ready to serve all our search queries, as well as be the platform on top of which we were building our large data stores. So this is the current design. It's still very similar. It's still an in-house rack design. We construct our own racks, and we use PC-class motherboards, and we use Linux, and we use pretty much our own in-house software, which I'll be talking about in a slide or two. A lot of the problems that we have has been over the last few years around power consumption, because the amount of money it costs to cool equipment is roughly the same as the actual the number of watts you need to provide to power the actual computer. So that ended up being a pretty large and significant part of our cost structure. So we started working with a lot of the chip design companies like Intel and AMD, and had a lot of discussions with them over the last few years to move away from these monolithic architectures, microarchitectures, to more of the Core 2 Duo kind of models, which actually reduces our power consumption quite dramatically. So this is what we do right now. So we've talked about the system, we've talked about the hardware in terms of where all our machines are and how they are being powered, and I'll be talking about the system infrastructure. The question here.
How many machines do you have now?
The question is, how many machines do we have now? Well, it's more than I can count on my hands. I think the number we publicly say is in the few tens of thousands. Any other questions? Yes.
I mean, you just mentioned that in order to give a better service, Google has do a great improvement of hardware. So my question is really the hardware is the necessary, is the key factor to provide better service?
So the question is, we've done a lot of innovation on the hardware end. Is hardware the key to having a good and a good platform on which we can build all these different services? And the answer is no, and that's my second part of my list of my talk about the system infrastructure, the actual software that we run on top of this hardware to make things more efficient and scalable. But yeah, hardware is certainly a key part of it. One of the key parts of hardware is that if we hadn't gone down the path of investing in these low-end PCs and compensating with it on software, then the company would have gone bankrupt. So in that sense, it's a very key and important part of our culture. Yes?
I have a question about the Linux. Did you do some kernel hacking on the Linux you use?
So the question is, do we do any kernel hacking on Linux? Yeah, we have certainly done a number of patches, and we have had some improvements to how we handle certain. I mean, there are certain stacks that have been modified over time, and in a few cases, we've actually contributed back to the open source as well. Yes.
You have taken any method of trying to be environmentally friendly with all the hard disk and hardware infrastructure you have built, and any considerations on the sustainable and reusable of the wasted materials like reusable hard disk and disposal, those kind of things?
That's a great question. So the question is how eco-friendly is Google, and what are we doing with all our hardware? It's a really good question, and I don't know the complete answer to that. I can give you some sense of what we're doing. We have been experimenting a lot with solar power, and especially on Google campus, I think we're going to have the largest solar array on campus, just to sort of see how we can power the computers that we have even within our buildings. A lot of what we do in our data centers is actually pretty eco-friendly, and I'm not sure how much of it is publicly known, but it's clearly a very important problem for us. We certainly have a lot of machines. We like to make sure that our hardware equipment is recycled and in a very eco-friendly way. All right, I'm going to switch to the systems infrastructure and some of the software that sits on top of the hardware, and I'll get back to. And that's going to be the last part of my talk, so I'll get back to some questions after that. So the goal that we have on the software end, again, to power all these wonderful applications and all the wonderful APIs that we have on top of this hardware platform, is how do we build out a very large-scale, very performant computing infrastructure. And we want to make sure that when an engineer joins Google, they have a very nice stack on top of which they could build out a lot of this functionality very easily. So it should be easy rather than hard to be able to come in and build out a very cool set of applications that you want to launch to an end user and have it scale, just keep scaling as more and more users actually come to it. So rather than thinking about post facto after a service launches, we want to make sure that we build it on top of a stack that we know is going to scale and has been proven to scale in a number of different applications. And also, we do focus on how does this actually enable better products? Because if you make it easy for engineers to do cool things, then engineers will do cool things, and that's really what our emphasis is, so that we can build out much better products for our end users in terms of better search results, in terms of better APIs, in terms of better storage models, and also to reduce the overall cost structure of the company, so that we can keep building out even more cool stuff. So I'm going to talk about a couple of these technologies that we have within the company. One of them is is GFS, the Google File System. So how many of you have actually heard about GFS? So okay, a few of you. So one of the first questions we asked ourselves is, why do we need yet another distributed file system. So given the amount of data that we have and the number of machines we have, we wanted to make sure that it was easy to have a very scalable file system into which you can throw in hundreds of terabytes or petabytes of data without actually having to worry about it as an engineer. So we wanted to make sure that the read-write bandwidth of the file system was just incredibly high, so that we can power all our core applications in terms of search, or in terms of Gmail, or in terms of calendar, or any of our crawling systems, or any of our different pipelines. And also is reliable over many, many thousands of machines. This is another huge part of what we do, because every machine has a number of disks, and we have to solve the problem. We don't want to solve the problem on a per application basis of worrying about striping across multiple disks. We don't have to worry about reliability in terms of when a machine goes down. How do we replicate content across from one set of pages to another? All these things are very important for us so that we can build out these scalable applications. And also, the other key difference that we have from the more classic file systems is that we typically have larger data blocks that we want to write. And as you all know, writing bigger disk blocks is actually much more efficient than writing smaller disk blocks and doing lots and lots of seeks to write the actual content out. And also, we want to make sure that we had very efficient operations that we could run in a completely distributed fashion across multiple data centers in multiple regions, and still make sure that the interactivity and response time is actually very low. And we had a very good advantage. Unlike other file systems, which have to be broad and general purpose, we know exactly what we run in our data centers. We know exactly what libraries we can control, what version of Linux we run, what patches can we issue to Linux. So having a lot of that control and having a very good understanding of our applications helps us design a much better file system that makes sense for us, rather than reusing an existing file system. Plus, it's also a lot of fun to build your own systems rather than reusing someone else's, so which is another huge motivation for this. So this is roughly how the GFS system actually works. It's pretty intuitive. It makes a lot of sense. It's a very simple design. What happens is we have a number of clients, and the clients you can see are on the right-hand corner. These are the miscellaneous servers, and they talk to a GFS master. This is the master which knows where the replicas of given content is. And at the bottom, you have these chunk servers. Imagine taking a very large file and breaking it up into much, much smaller disk blocks, like, say 64 megabytes or 128 megabytes, and having that striped data across lots of different machines in a given data center. Here's an example where I have C0, which is in yellow. That's one of the chunks. So given the terabyte of data, we've broken it up into a terabyte divided by 64 megabytes worth of chunks. And we've striped that chunk, C0, which is the very first chunk, into a couple of different servers at least. In this case, it's in chunk server 1 and chunk server n. Similarly, you see C5 being replicated across multiple of these machines. So what really happens is whenever a client needs to access a given file or a given portion of a file or a given set of chunks in a given file, it goes and talks to the master, which has a mapping of all the replicas, the location of the replicas, along with how heavily loaded are the machines. And that information is in the master, and clearly, as you might imagine, there is some master failover to avoid single points of failure. But once the master gives back that information to the client does some caching, and then it goes and retrieves the actual content in a peer-to-peer fashion from the chunk servers. So the master does the management of the metadata, and the actual transfer happens between the chunk servers and the clients directly. So that's roughly how GFS works, and it has gone through a number of revisions over the last few years. I think we are on version 4 or 5 right now. And a lot of this is interesting because it's one of the very few file systems that has been distributed to many thousands of machines and has proved to be scalable and reliable. And I think we have an anecdote that we have lost exactly one chunk out of all the many billions of chunks we've thrown into this mix ever, because of the incredible reliability of the GFS system. So that's one layer of software. Now that we have GFS, where we can store into it several petabytes or terabytes or hundreds of terabytes of information into it on any given application. So Gmail can do this, or ads can do this, or Google search can do this, or whatever, or Maps can do this. Now the next question to ask is, what are the interesting computations can we do on top of this data? So we have an incredible source through which we can access all this data. So what do we do with it? And there are a couple of interesting ways of thinking about the problem. One of them is actually a computational model, and it's called MapReduce. It's a very easy way to partition your problem or any computation that you want to do and push it to a whole bunch of machines in an easy way that can scale very efficiently. That's really the motivation behind MapReduce. And in terms of it's a programming model. It still uses C++ as the programming language, but it's just a way of thinking about the problem and pushing out computation. So there are two steps in this. As you might imagine, there's mapping step and there's a reduction step. So conceptually, what happens in the mapping step is we aggregate all keys and values that correspond to a given, just make sure. Yeah, we aggregate keys and values so that we map every single key that has a given set of values onto a single set of machines. And we coalesce them and we push them around. We imagine thousands of nodes just communicating with each other, pushing data around. So that's the mapping step. Now after that, there's a couple of other interesting steps along the way. But I would refer you to the MapReduce paper. You can just go to Google and search for that, and it's a great paper to go and read about. The reduction step is really about applying some interesting computation on top of the values that have been accumulated into a certain set of machines. So you have, say, a machine which has all the values associated with a given key. And what is an interesting computation you can run on top of that? You can do simple things like addition. You can do a median. You can do a mean. You can append. You can just take all the values in that and then append all of them to produce some other interesting results. And also you can chain a lot of these MapReduces. You can actually you can process huge amounts of data and partition the problem and produce interesting views on top of the data and then store it back into GFS. And you can run another MapReduce on top of that. And you can keep chaining multiple of these things to produce more and more interesting data that we can use to make our searches better. An example could be spell correction. So spell correction is on Google really works by using all the search queries that come into Google rather than going and looking up a dictionary. So in that situation, we have to go and process all our terabytes of search logs to figure out what are people doing within a given session, or how do they refine their queries, and computing back the list of queries that are very similar to the original query that the refinement actually happened. And that's an example of how you could take a whole bunch of map reduction steps and compute an interesting data that you could offer to our customers. Bigtable is not a computational model. It's more about it's a different way of storing and accessing data on top of GFS. So GFS is just a flat file system. It has a notion of files and the notion of chunks. You can store whatever you want to do into it. But GFS doesn't have the notion of a lookup model. You don't have a key value lookup like you would have in a hash map or in a hash table. So Bigtable was really designed as a large-scale storage system for really semi-structured data. And there's a very good paper on this. And I would encourage you to go and read that too. You can just go search for Bigtable, Google, and you'll find the paper. So the model here is it's a key value lookup. So any key that you want to store and any value that you want to store, you can think of values as just a whole bunch of different columns, and you can manipulate the different columns at different points in time. Some interesting transactional semantics around that. But that's really what Bigtable is about. So I've talked about a number of different things. I've talked about in the system infrastructure. It's all tied in because we need to have a very nice infrastructure, a stack on top of which we build our applications in an easy way so that it's scalable and reliable. And some of the elements of that are GFS, which is storage, MapReduce, which is a computational model, Bigtable, which is a storage and lookup model. And all the application that we build use this as building blocks for powering whatever features they want to build or whatever needs the user has. And a lot of this rolls up into the hardware platform, and the hardware platform is seamless to all the applications that we've built. And ultimately, the application that we have all tie in, and you should be able to access any of your content and modify it. You can store things back into it using a list of APIs. And a lot of the discussion later today is about how do you use Gdata, how do you use GWT as a way of enabling these interactive applications. And so I would encourage you to go and try out our applications and APIs and build out these cool mashups and build out sitemaps for your sites and make the web, in terms of the plumbing that we have for the web, a lot more interesting, a lot more comprehensive, and a lot more accessible to your friends and to your community. Thank you. I'll be happy to take any questions.
Thanks, Shiva. 如果有问题的话，可以用英文或者中文提问。OK。等一下麦克风。这边，这位先生。
Hello. I have a question. What kind of database be used in your large cluster? And the second question, how to join the load balance, high performance computing, and the high availability cluster in your large hardware?
So the question is about what kind of databases do we use in our large systems. Most of what we use in terms of storage and in terms of how we access the content within the company is through a lot of the things that I just talked about in terms of the storing our data into GFS, making a big table on top of that to access our data. And the reason why we do that is because databases have a number of different problems. I mean, there's a limited query language. There's a lot of issues around how do you scale those things. So what we do is we end up building out these interesting stacks of systems infrastructure within the company that we end up manipulating. But also, we have some parts of the company that use open source software like MySQL in certain very specific cases where transactions are much more important and scaling is not nearly as important.
We have another question right on paper. How can I use GFS and Bigtable directly?
So the question is, how can I use GFS and Bigtable directly? A lot of that is not really exposed to the rest of the world. I talked about them because this is to give you insights into how you can use the APIs as a way of storing and accessing content and all the different applications that we talked about. But ultimately, all the backends that we have in terms of GFS and Bigtable are all abstracted away by these APIs that you can end up using. And a lot of the information about the APIs is on our webpage. You can go to code.google.com and check out a lot of that information.
存在大量的 socket 操作，在这个时候是如何保证这种 socket 它这种网络的利用率，以及如何保证它的性能的，这是第一个问题。第二个问题就是说，对于 Bigtable 来讲，它是一种这种是只增量的存储，还是一种随机 I/O 存储？如果是只增量的存储，那么它对于这种修改操作是如何处理的？如果是随机操作的存储，那么它如何保证它的这种随机命中率？谢谢。
He had two questions. One for the GFS. He said in GFS there must be many socket operations, but for those two lots of socket operations, how can we ensure the operations will be have high quality and will use the bandwidth, network bandwidth? That's the first question, and his second question is on the Bigtable. Is Bigtable a read-only table or randomly accessed table, sequentially accessed table, and if it's not a randomly accessed table, how we ensure the performance of the big table?
Okay, so let me take the first question first about GFS and how do we make it scale and how do we make it very performance oriented. As part of the design, there are a lot of things that we do to make sure that the amount of bandwidth that is being transferred is not very high. So for example, the client talks to the master and gets back metadata that says that here's a list of all the servers on which my chunks exist. But after that, the communication of the actual chunks, the 64 megabytes or 128 megabytes that are stored on the chunks, that communication happens between the client and the chunk server directly. So the amount of bandwidth that is being transmitted is as much as you need, as much as the application needs. So we don't go any worse than that, and we don't get any better than that either, as would make sense. In terms of reliability, we certainly have enough replication of chunk servers and enough load balancing of chunk servers so that if a certain subset of chunk servers are dead, then there's active amount of work that the master does to move chunks from one set of servers to another set of servers and manipulate its own data structures internally, so that when the next client comes in to ask for a set of chunks, it knows how to route the request in an appropriate way so that the client doesn't notice any of this. So all this is seamless to the client. So the client just sees, hey, let me ask for a chunk and I get it back ultimately, or get the metadata for it back. And a lot of the active management actually happens in the background to the master, and by enough monitoring and by enough statistics, we can figure out what is really happening in the network. So that's the GFS story. The big table question was about...
the method of the operation to access the data is the sequentially accessed or the randomly accessed, and how to ensure the performance.
Yeah, so big table is also built on top of GFS. So imagine these interesting structures that you... so the first part of the question was, is it actually a read-only system? No, it's not. It's certainly it's a read and write system. And the operations aren't happening on a single machine. It's really happening on thousands of machines. You have thousands of these tablet servers, smaller big table servers, which are doing all the manipulation themselves in terms of reading and in terms of storing. So it's all distributed. So in that case, we don't have maybe as much of a challenge. It's not on a single machine. But clearly, as you have, if you increase the number of requests by a factor of 10, then you run into all the usual problems with load balancing, and then the question will become, how should I have a different access pattern? Should I have a different, should I locate my data together? Should I increase my number of machines by 10x? All these things are the usual options that we will consider.
因为时间有限，我们想最后2个问题吧。
Is a quite successful company, and so the cost should not be the first priority. And I want to know why don't you choose to build your service on more reliable or professional clusters like Unix or some other operating systems?
So the question is more about hardware. We certainly use Linux as our OS platform on top of which we build our application stack. But in terms of hardware, we've noticed over time that the mean time between failure of all the different components, independent of whether it's an ultra-reliable hardware or not, is not that interesting to us. So we rather would prefer to compensate for it by building a software stack that'll just make it seamless to the application. If the data that you have is moving around from one machine to another machine, and the application doesn't know about it, then that's very good, because you know that machines are going to die anyway. So we've noticed that the NTBFs of the different components are such that it makes sense for us to just build out these cheap hardware and just compensate for it.
So don't you meet any kind of troubles when using Linux? Like we meet every day.
Do we have any problems with using Linux? Well, the great part about Linux and open source is that if there's a problem, you can go in and figure out what the problem is and fix it. That's not something we can do with other server platforms, which is why we use Linux.
Okay, thank you.
Okay, I think this is the last question.
From the paper, we know when write or append operations fail, the client retries the operations. Why not let the primary chunk server do it? I'm sorry, I'm just trying to parse this. We know when, right? So why not let the primary chunk server do it? Oh, I see. Okay, so the question is, if we, in GFS, if the client is trying to do a read or a write, and in that case, the client retries the operations, because there's a client and there's a master and we have the chunk service. So the client actually ends up retrying the operations. So the question was really, why can't we let the primary chunk server do it? So there's no notion of a primary chunk server, because if you start having primary masters and primary chunk servers, then if you have any a master and a slave relationship in any of these distributed systems, then you have a leader election problem, then you have to worry about what happens when the primary goes down, and then who shares the metadata. So rather than doing all that, we try to keep all our chunk servers to be equivalent. They all are first-class citizens in whatever they're doing, so they don't have any extra information. So there's no notion of a primary chunk server. So it makes much more sense for the client to do it. The only place where we have a master is in the GFS master, because it's a much fewer number of machines. So problems are network partitions and leader elections is much easier problem. So we can address that. So it makes much more sense for the from a simple design standpoint, it makes much more sense for the client to retry whatever it does.
Okay, I think we should have considered this very last question, since it's very interesting about yourself.
So I have a personal question. What's the main reason you joined Google in 2000? Well, Google has been an interesting company. I knew Larry and Sergey from Stanford. We were in the same lab, and we were doing our PhDs together. And so I was a Google user from day one, from '97 when the service started up. And so it was great to sort of see its evolution. It wasn't clear at that point whether it was going to be a successful company like that. It is clear that it was going to build out a very good product. But in terms of there are very few technology companies out there. If anyone is interested in computer science, then it's a great place to be at in terms of solving these large, hard, world-class problems, and also to have impact on millions of people. And that's really why I'm at Google. The other question is, any suggestions on stepping into open source development for 2 to 3 years, but dream to join Google? Yeah, having interesting projects is always something that we look for in joining the company. People who have a passion for doing big things and have a lot of creativity impact the world at large are folks that we certainly look for in joining Google, and open source is a great way by which people have actually come to us. We also have a lot of interesting events that some folks will be talking about later today in terms of the Summer Code of Jam program, as well as what interesting open source projects that we've been sponsoring over the last few years. So yeah, Google is it's a wonderful place to be at, and we're certainly hoping that a lot of you will be using our APIs and platforms and giving us more feedback about what we should be doing so that we can build out world-class products for you as well. Thank you.